Okay, last week we used this circuit to develop the accurate formula to calculate compressed power sent from one end to the other end through a transmission line. So this circuit is very general, with impedance having both resistance and reactance, and two sides will have two voltages. We don't worry about whether they're load or maybe a source, but we know the voltage phasor V1 and V2. So they may have different magnitude and different angles. V1 can be leading V2, or V1 can be lagging V2. So finally, we have two general formulas for the active power and reactive power. So we depend on the magnitude angles of both voltage phasors. And then we have those two formulas for the cases without loss, which means R will be 0. So that will make this formula simpler. So, and we can utilize those two formulas to understand how active power is delivered. So from the first formula, so the sign of P12 depends on which angle is higher, right? So if V1 is leading V2, so active power will be from left to the right. And the reactive power, because typically the delta can be small. In most of real systems, the delta will be less than 15 degrees. I mean, if you compare the angles of each maybe transmission line. So mainly this part will be pretty close to 1 because this angle can be very small. Then, so the which magnitude is higher will determine the direction of reactive power flow. So active power flow is coming from the high angle to the lower angle. And the reactive power flow is coming from high voltage to low voltage. So that's what we concluded using this simple case. Just to summarize, so if we don't consider any loss, active power will be opposite between the two ends of the line, and reactive power could be same because both reactive power will be coming to the middle if the voltage are very close. So when the angle difference is small, typically less than 15 degrees, so you can calculate sinus 15 degrees will be very close to the angle itself. So even you consider 30 degrees, the 30 degrees is still, if you calculate it, it's not too different from the angle itself. If we use the radian for angle, and cosine angle will be very close to 1. And for 15 degrees, that error is only about 1% or 3%. It's a pretty good estimation. So if your angle difference is between 15 degrees, so you can use the angle itself to estimate the sine angle. And so cosine angle will be roughly 1. So which means active power is roughly proportional to angle difference. Direction of real power flow will be mainly depending on the angle difference between the two voltages. So if V1 is leading V2, angle difference is positive, and active power will be from node 1 to node 2. The theoretical maximum power transfer really depend on this value because the maximum value of for this sine angle will be 1. So this one is always less or equal to 1. So this factor really determines the theoretical maximal active power you can deliver through any transmission line. So when you open the angles difference by 90 degrees, that will be the theoretical maximal power transfer. So usually we call this part as static transmission capacity or theoretical static stability limit. Reactive power will roughly proportional to the voltage difference. So if you want to send the reactive power through over transmission line, you only need to increase the sending end voltage magnitude. So I will use this as a practical example to show how we can utilize the simple conclusion we got from previous slides. So we utilize the angle sensitivity to monitor the energy exchange between two substations. So this is from the screenshot of real-time monitoring software. So which collect data at different substations. And a draw the arrow does indicate the energy change. So this one tells the energy is coming from the right substation to the right substation. So you see the large arrow. And for this specific system, this is, if you can recognize the background, it is about the western connection, the western side of the US. So here is California, and this is Oregon State and California, and they monitor the power exchange between the Oregon substation and one California substation. For this case, the power is from Oregon to California, and for this case, this power is from the east to the west. And for this specific system, and they utilize this sensitivity. So for every 0.6 degree angle change between two substations, the power exchange will increase by 100 megawatt. So for this case, they can easily just monitor how the power flow is going to change. But to calculate the more accurate power change, we'll have to wait until session number 6 when we talk about power flow. So that will give you more accurate calculation. But for this example, just give you an idea, even we only know that very simple relationship, we can utilize that relationship for many like monitoring applications. And this chart indicates a very linear relationship between the angle difference and also the power change. It's pretty linear when the angle is small. So this is the last slide of the single phase AC circuit. So next we'll move to three-phase circuits. So for three-phase circuits, and if we have, so first here we consider balance condition and the steady state condition. So in this course, we don't consider imbalance between any 2 or 3 phases, and we don't consider any contingency. So when we draw a three-phase circuit, we really mean 3 very symmetric single-phase circuit. It just lay out with angles, one angle displacement by 120 degrees. So for instance, we can put 3 identical single-phase circuit together, and they have identical load. So each load will have impedance Z with magnitude and also angle theta. So theta here will be the power factor angle. So cosine theta will be power factor. And next, we assume the 3 voltages are generated by the same generator, because the 3 windings ABC will have a 120 degree displacements. So if we use a phasor diagram, we consider positive phase sequence, which means the phase A will be leading phase B, and phase B will be leading phase C. And here we use phase A as a reference, so we can assume this one will have angle 0. So this one will have angle 0. And then phase B will have a negative 120 degree because it's lagging A. And the phase C will be lagging phase A by 240 degree or leading phase A by 120 degree. Okay. So why is B lagging A? Because ABC correspond to 3 windings in the generator. So when the rotor revolves counterclockwise, it will first face A first. Then after 120 degrees, it will face phase B. So when we go to the generator modeling section, we'll look into the inside of the generator to understand how the voltage is induced. But right now, we just assume A is leading B, B leading C. When you took a 325, you may learn like a negative phase sequence, because sometimes if you study the motor, you want to reverse the direction of rotation. So you want to switch 2 phases. But here in generator, we always assume A is leading B, B is leading C, so which is positive phase sequence. So then we can write down the phasors for all the three phases, because we use phase A as reference. So that will be 0 degree, and B will be negative 120, and C will be positive 120. Because we know the power factor angle, so current for each phase will be will have a power factor angle lagging the corresponding voltage. So such that the IA will be negative theta, and so IB will lag VBN by theta, and similarly, so IC will be lagging VCN by theta. And next, we just plug in those voltage current phasors into the formulas we proved. So previously, we studied the single phase instantaneous power. Right now, we just need to, so this is the single phase instantaneous power formula we proved. Next, we just need to apply the formula to phase B and phase C, and we add them together because we want to calculate total instantaneous power going into the three-phase load. Assume the total power is supported by a single generator. So let's say this is a three balanced load of three phases, but they all powered by the same source. So this instantaneous power will tell the total power coming out from the source. Okay, so when you write down those three lines, and you noticed the three lines will have basically the same form. The only difference is the second line will shaped by 240 degree. Okay, this 240 degrees come from 2 times 120 degree. And the third line will shaped by positive 240 degree. So when I add all the 6 items together, so all the cosine item will cancel out, and all the sine item will cancel out. So eventually, whatever is left is only this part. That will generate a very simple formula. So under static condition, the instantaneous power delivered to a balanced three-phase load is constant, which is simply this one. So you can recognize this formula. This part look like the active power for single-phase circuit, and the 3 just multiply the single-phase circuit active power by 3. Okay, which means if we know the active power for phase A, phase B, phase C, we can use any one, right, to multiply by 3. And this is also simply just, we call this one the 3-phase active power. So for steady state condition, balanced 3-phase circuits, the 3-phase instantaneous power is identical to 3-phase active power. So next, because the 3 loads are balanced, so the current because each current will be lagging the corresponding voltage by the power factor angle. So which means when we put the 3 current together, they have to be canceled out. So which means if we connect those 3 lines, we just short circuit those 3 lines. So the total current will be 0, which is equivalent to just remove this line. So just get rid of those 3 lines. Any question?
Explain how you got rid of the signs algebra.
Okay. The first thing is, if you are really familiar with formula, to spell this one out, this is because cosine angle 1 minus angle 2. You just use the label to just spell out this formula, and finally they all cancel out. So that's a simple explanation. If you use the formula, and similarly use here is same, use simple formula. But another way to explain it is just you treat this cosine angle as the real part of complex number. This is the imaginary part of complex number. This is just magnitude, right? This is like imaginary part of some complex number. This is the real part of complex number, but lagging the first complex number by 240 degree. this is lagging by 240 degrees. So which is like you are actually submitting 3 complex numbers. The first one will be pointing to here. And second one is lagging 240 degrees, which is, right, should be pointing to this direction. The other one is leading 240 degrees will be pointing to this direction. Okay, that's a geometric way to explain why those 3 sine terms and cosine terms, they all cancel out. Yeah, sure. Any other question? Yeah, okay. All right, so which means if we use AC source to power balance the AC 3-phase load, we don't need the 4 transmission line. We don't need the 6 transmission line. And we don't need the 4 transmission line either. We only need 3 transmission line. So which is very efficient. Just 1 line for each load. So that is why when you look at any tower, high voltage tower, you only see you need to first recognize the insulator, because not everywhere is transmission line. So you may see many wires there. It can be on top and bottom, but somewhere doesn't connect to a insulator. So only this line is connected to 2 insulator to the tower. So that's could be phase A, phase B, phase C. So you only have 3 lines. You don't see the neutral line. The neutral line is just the ground, because for balance condition, there's no current coming back. So instead of build another line connecting all their neutral point, it just directly connect to the ground. But definitely they need to deal with any contingency. If there's a fault, if there's a short circuit, what if this line is going to the ground? It's not balanced anymore, but they need to deal with that. But in this course, we focus on only 3-phase balance condition. I have to ask the question, where is the reactive power? So we prove the 3-phase instantaneous power is identical to the active power. But where does the reactive power go? Reactive power is some signature making the AC circuit different from DC circuit. So for AC circuit, when the voltage, current, the sinusoidal waveform, they're not having the exactly same angle, because here we never assume the power factor angle is 0, because theta can be non-zero. So it has to have some reactive power. So if we assume theta is non-zero, so the current will be lagging the voltage. So there will be reactive power, right? The reactive power is supposed to be equal to this is apparent power multiplied by sine theta. So there should be some item which is 3 times apparent power multiplied by sine theta. So that should be the 3-phase reactive power. But for this case, it's gone. Any thought? All right. So here we just assume the 3 loads to be balanced, identical, but we never look into what is inside of each load. So the 3 loads can be from 3 feeders going to different regions for different customers, right? So if you look into each individual load, each load will have reactive power. It still have reactive power. You just use a formula which is apparent power multiplied by sine theta. So the answer is 3 loads, each of them will have some reactive power. But when we put them together, if those 3 loads are not they stay together, such as this can be a just 3-phase motor, okay? And if we only just calculate from the outside, we calculate one source powering a motor, and it looks like the motor doesn't consume reactive power. It only consumes active power, because the reactive power for the 3 phases, they balance each other. But if you look inside of each load, it still have reactive power, okay? So which means the reactive power is not, it doesn't never disappear. It will stay inside of each load. Okay, so in the following slides, we'll go through a few typical circuits and to prove some formulas. I believe most of them might be familiar to you, if maybe after you learn from circuits or other courses. First, let's continue on this Y-connected load. So Y-connected load, but here we add the neutral line, just in case there's current. And so we call the voltage on each load, each ZP as the phase voltage or line to neutral voltage. So that is same thing. And here we use VAN as a reference. So we just call this one basically the phase voltage, the reference phase voltage. If we draw the phasor diagram, VAN will have zero angle in parallel with the real axis, and VB will be lagging VA by 120 degree, and VCN will be leading VN by 120 degree. If we draw another phasor, which is in parallel with the VBN, but pointing to a different direction, opposite direction. So this is actually represent negative VBN. So we draw this phasor because we want to figure out the voltage difference between two phases, between two lines. So next, we want to find the line voltages, which means line-to-line voltages, such as VBA, VAB, VBC, and VCA. Okay, so when you so in the circuit, when you write down the voltage phasors, pay attention to the subscripts. Okay, because for instance, when we call it VAN, so both A and N have purposes, because VAN represent how the A side is higher than N side. So that's why we put A in the front. You can call, if you create another phasor, which is VNA, which will be opposite V to VAN, right? So what that means, so VAN basically just tell how much the A side, because we call this terminal is A, this is N, right? That make it clear. So this is A, this is C, and this is B. And this is N. So for the source side, this is also N because that's connected through a line. And this terminal is A, capital A. This is capital C, and this is capital B. Okay, so now it's clear. So for the voltage phasor VN, which means the voltage difference between A and N, how much A is higher than N. And the VNA is, there will be another one, which is could be VNA. This will be negative. It will be opposite. Okay. Similarly, when we see something like a VAB, which how much A is higher than B, and which is negative VBN. So now we draw a phasor here. This will be a negative VBN, which is equal to VNB. So this is just similarly VNB. Okay. So be careful with those the subscripts. So next, if we want to know what VAN is, so VAB will be equal to how much A is higher than N plus how much N is higher than B, right? This is a Kirchhoff voltage law. And N is something in the middle. So how much A is higher than N and how much N is higher than B. So then we will know how much A is higher than B. So VAB is just simply this phasor, which is equal to VN minus VBN. Because the second item is equal to negative VBN. So when you swap to a subscript, you have to add negative sign here. So this voltage will be equal to positive VN plus negative VBN, which means VN minus VBN. So this will be VAB. And from this figure, you know this, based on the triangle, this is 120 degree, and those two angles are identical. Each is 30 degree. And the VAB will be leading VAN by 30 degree and also multiply by factor of the root of 3. Similarly, we can get the formula for all the other the other two line voltages. So for instance, VBC will be VBN minus VCN. Okay, which will be, if we know the VBN this phasor and VCN this phasor, so to calculate the subtraction of one phasor to the other phasor, you just draw a phasor starting from the second one going to the first one. So you draw a vertical phasor pointing to the ground, which is this one. So it doesn't matter you move the phasor. So you can move any phasor to the. It doesn't have to be start from the origin, but as long as they have the same length and pointing to the same direction, so they'll be identical phasor. So those we move this phasor here, so that will be VBC, and this is negative 90 degree. Similarly, you can get the phasor of VCA. Okay, is this clear? All right. So next, we can get those two formulas. So when we study a Y-connected load, the line-to-line voltage will have magnitude equal to the root of 3, which is about 1.73 times the magnitude of the phase voltage. And the current will be same because the current on the line will be the same current going to each load. So the line phase current will be equal to line current, but line voltage will be 1.73 times the phase voltage. And you can utilize the Kirchhoff voltage law to calculate the voltage on the source side because you know the load voltage, and you also know this is the voltage drop along the transmission line, and this is voltage drop along the internal impedance of the source. So you can calculate source voltage. Similarly, on the source side, the 3 voltages also have 120 degree displacement in the positive phase sequence. Next, we want to get the phasors for the phase and line currents. For the Y-connected load, the currents going to each phase will be same to the current going to that line. So IA will be, we just call this one to be the phase current, and to calculate the current, which is equal to the voltage, phase voltage divided by the load of each phase. Okay, so which will be, we'll have the angle negative theta, which is theta is power factor angle. Then we can get the currents for phase B and phase C. So we know all the line currents are have the same magnitude, which is equal to the magnitude of each phase current. So balanced 3-phase power system problem can be solved on a per phase basis for phase A only. So we don't have to always draw this 3-phase circuit. We only just pick this circuit, which will come to this single phase circuit. Okay, because whatever you calculated on this circuit, you get voltage, current. You can easily get the voltage current on phase B and phase C. So you only just study the system as a single phase circuit. Then you duplicate the answer, make some modification to get phase B and phase C. So we only just need to utilize Kirchhoff voltage law for this circuit. So how about the balanced delta connected load? So balanced delta connected load will have the line-to-line voltage equal to phase voltage. So which means if you measure the voltage on the line, which will be same as the voltage you measure on each phase. To draw the phasor diagram, we'll use IAB, which is current from A to B, as the reference. So this will be the phase current. IAB will be the IP phase current, and IBC will be lagging phase A by 120 degrees. Y is lagging because B is lagging A by 120 degrees. C is lagging B by 120 degrees. When we change the two subscript from AB to BC, the current has to lagging the first current by 120 degrees. Okay, then ICA will be leading AB by 120 degrees. And next, from the Kirchhoff current law, we know if we look into this point, so there's a one current coming in, which is IA, right? There's a two current coming out. Oh, sorry. Yeah, there's two current coming in. One is IA, the other is ICA. And there's a one current coming out, which is IAB. So, which means IAB will be equal to IA plus ICA. Then we will have this formula. IA will be IAB minus ICA. So based on the symmetry, we can get the other two formulas to calculate the line current from phase currents. So to calculate what is IA, so we want to find IA in the phasor diagram. We know the IA will be the difference between the IAB and ICA. So we need to first, which will also the sum of IAB and the negative ICA. So we draw the negative ICA phasor, which will have the same length as ICA, but pointing to a different direction. So then we calculate the sum of the two phasor. We just start from its origin, the end of the first phasor to the height of the second phasor. So that will be IA, okay? IA will be lagging IAB by some angle, which is 30 degrees. Oops. Okay. This is 30 degrees. Negative 30 degrees. So if we know IAB, we just know the IA will be lagging IAB by 30 degrees, and also the 1.73 times longer, or 73% longer. And we can draw IBC and ICA. So from IAB, if you know IB, we can directly write down the expression for IA. Similarly, that we can do that for IC and IB. So IC will be upright with 90 degrees, and IB will be lagging the IAB by negative 150 degrees. So one is 90 degrees, this 150 degrees. Okay, so we know the line current will be 1.73 times phase current. Next, we talk about the transformation between the delta Y connection. I assume everybody have been familiar with this formula, but here we use phasor diagram to redevelop the formula. Just show you, so if you forget some formula, you can easily use phasor diagram to help you to find the correct one. Assume we have the three same currents as the same balance current going to two different loads. And the first one is delta connected, second is a Y connected load, but they're all balanced. So for the first load, and so IA, from the previous slides, we know that IA will be IAB plus IAC, because that will be based on Kirchhoff current law. IA will be equal to the current from A to C plus current from A to B. So here's IAB, here's IAC. So this part is just simply applying the Kirchhoff current law to the node, the nodes A. And for each phase, we have the voltage, phase voltage divided by the impedance of each phase. And then we simplify that the numerator will become the sum of the two line-to-line voltage phasors. So we want to understand what this phasor is, so we can utilize the phasor diagram. So in the phasor diagram, we draw, we use VAN, the phase A voltage at the reference. We have proved VAB will be leading VAN by 30 degrees, right? VAC is symmetric about VAB, will be lagging VAN by 30 degrees, but they have identical lengths. So what is VAN? VAB plus VAC. So that will be, we will draw a parallelogram. So this one will be the sum of the 2-volt line-to-line voltages. So this will be VAB plus VAC. Okay, so what is this one? So based on this geometry, we know this triangle has 60 degrees on each angle, right? So which means those three edges are same, also equal to those two edges. So this is 120 degrees, and which means this angle is 60 degrees. So that means if we call, let me make it clean up. So if this part is 1, okay, and what is this part? This is half. And this part is also 1 plus a half. So the total is 3. So this line is 3 times of each edge. 3 times of the VN. You can use the complex number to prove it. So you just calculate the summation of VAB and VAC because you already know the phasor representation of each voltage. You calculate the sum. You change each one into the form of the real part plus imaginary part, and the imaginary part cancel out. So finally, you get 3 times of VN. So you can either use the geometry to prove it, or use just complex numbers formula to prove it. Okay, so we know the line current is just 3 times of phase voltage divided by the load on each delta connected phase. So for Y connection, it will be simply just the phase voltage divided by each phase impedance. So we can immediately get. So if we want to change the delta connection to Y connection, we simply just divide each delta connected load by 3, and we put it on each phase of the Y connected load. So we're going to use this formula to finish some calculation. So next, we want to extend the concept of the complex power of single phase to 3-phase systems. So we already defined the 3-phase IT power, which is simply equal to the IT power of each phase and multiplied by 3, right? So we can also define the 3-phase reactive power as 3 times of the reactive power for each phase. So this is just defined. We just define in this way, which means we can put the P3 phase and Q3 phase into the real and imaginary part. So we will get this complex power for 3-phase circuit. To calculate this 3-phase complex power, you can calculate the complex power for each single phase, then multiply by that one by 3. Okay, so this is the correct formula to calculate the 3-phase complex power. But sometimes you have to assume either Y connection or delta connection. Okay, and to calculate 3-phase complex power, you're going to utilize whatever can be measured directly. For instance, if the load is a Y connection, the phase voltage equal to line, phase voltage will be the line voltage divided by 1.73, but phase current is equal to line current. But for Y connection, the phase voltage is equal to line to line voltage, but phase current is equal to line current divided by 1.73. So how can we utilize the measurements to calculate three-phase compressed power? So if we use the line-to-line voltage and line current, because which are more easily measured, we can prove the three-phase IT power will be the root of 3 multiplied by the product of line-to-line voltage and line current and power factor. So this is because when we translate this one here, and for the phase voltage, that has to be replaced by the line-to-line voltage divided by 1.73. So this factor will cancel with this 3 by 1.73. So there's 1.73 left. Similarly, so if you use line-to-line current and voltage, so the product multiplied by sine theta, then multiplied by 1.73 will give you reactive power in 3 phases. So theta here is actually the power factor angle, which is the angle by which the voltage is leading current in the same phase. Okay, sometimes you may, when you measure line-to-line voltage, you can maybe measuring the voltage between phase A and phase B. And when you measure the line current, you may pick line A to measure the current. And you have the waveform, and from the waveform, you can get the phasors. So there's some devices, they can directly give you the phasor. They give you both magnitude and angle, okay? Because you know the voltage phasor and the current phasor, is this correct to use this formula to calculate compressed power? So VAB is you measure the line voltage between A and B. So assume you can get this phasor directly from the sensor or measurement device. And IA is the current phasor you measure directly on line A. Because we earlier in the single phase circuit, we define compressed power as the product of a voltage phasor and conjugated current phasor, right? Can you do this one? Because from here we know we only just need to multiply the product by 1.73. So is this one correct? You cannot do it. You know, this cannot be correct. Why? Because angle is really when this formula is correct, the angle you have to take the angle by which the voltage is leading the current. So this formula, you have voltage multiplied by conjugated current. You assume this current will have angle lagging this voltage by theta, but which is wrong. The IA is not lagging VAB by theta, it's by a different angle. So if you calculate this one, that will give you wrong answer. So if you can try, you can assume maybe any voltage phasors, you use this formula to calculate compressed power. You calculate real part, imaginary part, and combine them to be the compressed number as compressed power, or you use this formula. So the second formula will give you wrong answer. It can be explained using the phasor diagram. So if we draw the phasors A, B, C for voltages here, we use Vn as a reference. We already proved the VAB will be leading Vn by 30 degrees, and which is longer. So simply just draw this phasor because VAB will be Vn minus Vbn, which is equal to a phasor starting from the second head to the first head. So this is VAB. Let's draw the IA. IA is the current, which is lagging voltage by theta angle. So this is the current. Okay. And what is the angle difference between VAB and IA? We need to move this phasor here, right? But keep it parallel, and also same length. We just move the end of the IA from the origin to the head of VBN. So now you know the angle difference between VAB and IA will be this angle. If you also move So if you use VAB and IA to calculate compressed power, you actually assume this one will be the perfect angle, but actually it's not. So if you turn the IAB by 30 degree clockwise, so you'll get this purple phasor, which is IAB, and this means multiplied by a phasor which has length of 1 and angle negative 30 degree. So this will be turning the VAB by 30 degree clockwise. And these two phasors will have the angle which is theta. So it's okay to use this voltage multiplied by conjugated IA, then multiplied by 1.73. That will give you the correct answer of compressed power, because you have made this correction to make sure the voltage and current phasors are separate by the power factor angle. But this formula is wrong. So correct formula will be, so correct formula should be, you can use this formula, VAB, then you add a negative 30 degree, then multiply by conjugated current. If you use this formula, it's fine. And you can decide to pick, unnecessarily this current, you can pick IB, IC, and for the line-to-line voltage, you can pick a VBC or VCA, anyone, but there will be some angle you need to make correction to make sure the voltage, the current phasor is separate by the power factor angle. Okay, so next two slides will be, I will quickly go through one example from the textbook because this is similar to a homework problem. Not for this, the homework due this week, it will be next week. Because the homework due this week will be only on a single phase circuits, and the next one will add some three-phase circuit question. So there's one source connecting two loads. One is Y connected, the other is delta connected. And from our slides, we know if it's Y connected, we need to utilize this formula to calculate the phase voltage if we know the line voltage. But for this case, we do know the line voltage, which is 207, right? So we have to use the formula to calculate the phase voltage. And for the delta connected load, the phase voltage will be line voltage, but you have to be careful about the current. And sometimes you may want to translate or transform the delta connected load to Y connected load. If you do that, you just divide each load by 3. So that will give you equivalent Y connected load. Okay, so for this question, we need to calculate the current, the real power, reactive power from the source, and the line voltage of the load, and the current per phase in each load, and total real and reactive power in each load and line. Okay, so we will use this single phase circuit for phase A. For phase A, so there will be two loads. The first one comes from the phase A of from this one, from phase A of the Y connected load. But second one is unknown. This one will come from the transformed delta connected load. And we just go ahead to calculate the phase voltage, which is based on this formula to get 120 volts for each phase. And for the transformed Y connected load for each phase will be basically just this one divided by 3, right? So we'll get the equivalent of Y connected load. Then we can just do calculation as a single phase circuit. So current will be voltage divided by the total impedance will be 5 ampere. And compressed power, this one, it doesn't have a reactive power. So which means the two loads, one has inductance and the other have capacitance, they just cancel each other for the reactive power. Second, we can calculate the load on voltage on the load side. And then from this phasor diagram, and we can calculate from the line-to-line voltage, we can know the phase voltage. So this will be the line-to-line voltage on the low side. So this value is slightly lower than so this value. So the line-to-line voltage on the source side will be about 207, but on the low side is 193. So continue on this circuit. Next, we're going to calculate the current. So current will basically just first we calculate each current on each load. And from the phasor diagram, we can calculate the line current. So we'll use this formula to calculate line current. Finally, we can just calculate the three-phase compressed power. So three-phase compressed power has real power 1800 and 0 reactive power, and line loss will be the line impedance multiplied by the current square and multiplied by 3. Okay, so this is our last slides. From Friday, we'll start next session. So on Friday, there will be another quiz covering the section 2. Okay. So it'll be an open book test based on Canvas. So I will put maybe starting from 8 a.m. until the late afternoon.
Will be the same for the first quiz, like take or whatever.
On Friday, the second quiz will be on Friday.
Second question, the homework one that's due on Sunday, is there a possibility that we do Monday night in case I have any questions over the weekend? I can just.
Yes. Usually I give 24 hours. Which means I put the due date, which is a Sunday. I encourage everybody to finish before that Sunday night. But if you finish before the Monday night, that's good. That's fine.
Late.
No late. Yeah, because if I put Monday night, somebody will submit on Tuesday night. Okay.